Okay, continuing our brisk pace through the last couple chapters, we're going to look at Chapter 3 today. This is the first of two videos on Chapter 3. In Chapter 3, we're starting to learn about the interference of light. And so this is more of a wave approach to light, where in the previous chapter we were really thinking more about light as a ray. So the first thing that we need to do to understand some of the phenomena that we're going to study in this chapter is we want to understand what happens when two waves come to the same location in space and how do they interfere and what rules apply. This will help us then understand a really cool experiment called the Young's double slit experiment, which basically showed that light would act like a wave. We're also going to understand, how that produced an interference pattern on the screen. And then finally, one of my personal favorites, I don't know why, is that thin film interference. Basically, if we look at the next picture, explains why a soap bubble can look really cool like this with all the different colors. This is actually due to what we call thin film interference, where different wavelengths of light are constructively interfering at different locations, and that's why we see the different colors. The other example of the phenomena that we're going to be looking at in this chapter is the one on the bottom, the Young double slit experiment, where when you send light through two closely spaced slits, instead of seeing two bright spots on a screen, you actually see what we call an interference pattern, which proves that light is behaving like a wave. So the first thing we have to understand is what we call this principle of superposition, which I believe that we've talked about before. Yeah, absolutely, we did when we talked about standing waves. So the principle of superposition governs how waves interfere when they overlap in space. And basically the idea is that if two waves come to the same location in space, the resultant displacement at that point is just found by adding the two displacements of the individual waves that are at that location. You basically is like, how do waves interfere? You just add them together. So this picture shows sort of the two extremes of interference, which we call constructive interference and destructive interference. In the first part of the picture, we see constructive interference, and that is when two waves are at the same location and they're oscillating exactly in phase with each other, so that we see the peaks are occurring at the same time and also the valleys are occurring at the same time. So what happens if we add those two waves together through the principle of superposition, we get one wave which has twice the amplitude of the individual waves because they both had the same amplitude. And so because they're adding together in a constructive way, we call it constructive interference. At the other extreme is these two waves, notice they're doing exactly the opposite thing at the same time. When one wave is at its peak, the other one is in its trough, and vice versa. So when we add those amplitudes together, we just basically, the two waves cancel each other out. And we call that destructive interference. So as I said at the beginning of this slide, these are the two extremes of how waves can interfere. You can also have something that's sort of somewhere in between, somewhere along the spectrum between exactly having constructive interference or exactly having destructive interference. It's a continuous spectrum between the two. So just showing some pictures of how we like to visualize waves because it's helpful for us to understand what we're looking at. So this is just, in this first picture, we're sort of visualizing how waves are traveling from their point where they're created. So at this location, S1, we view that as the source of our wave. In a ripple pond, this might be a probe that is poking the water at regular intervals to produce a wave. And then we would see the ripples move out away from that source. And so the ripples are like the wave fronts we would call the wavefronts the crests of the wave. And so we only see the crests produced in this picture. So then the distance between two adjacent crests would correspond to one wavelength. Now, the reason that we wanted to show those pictures is because often we will use those pictures to illustrate how two waves can interfere. So now we've changed the picture, and there's two separate sources, S1 and S2, and you can see S1 has blue wavefronts and S2 has green wavefronts, and they both are moving out from those sources. We're going to make them in phase, which means if they were caused by probes hitting the water, they would be hitting at the same time. And so as these wavefronts spread out, they are going to be overlapping. You can see how the two colors, the blue and the green lines, are overlapping, and that is really what we're saying they're interfering. And so places, because we said that the lines represented the peaks, so like this location would be totally constructive interference, and then somewhere in between, like here, would be a place where they were destructively interfering. There's a lot of conditions that we've placed on these two waves. We said that they're monochromatic, which means they have a single wavelength and frequency, because if you think about light, the color of light is denoted by its wavelength or its frequency. And so we're saying that these two waves have exactly the same wavelength, and then of course they would have the same frequency. They're also in phase with each other, which means that they were being created at the same time. And then we also can call these sources of waves coherent. Coherent sources are monochromatic, so that means that they have the same wavelength and the same frequency. They're in a same phase relationship, so it means that the phase difference between the waves is always the same, and they're also, then we call them coherent. So as we go back, we're trying to think about how these waves interfere, and we mentioned that the locations where the two lines are crossing is a place where they're interfering constructively. And they've outlined some locations on this on this picture where they're interfering constructively. As for instance, at point A, the two waves are interfering constructively, but notice that point A is the same distance from both the sources, but another location, B, is another location where they're interfering constructively, and they're not actually the same distance from the two sources. And so that's going to be something that is pretty important to understand. So what we want to do is we want to come up with conditions for constructive and destructive interference, and basically what we find is that the path difference, and when we say the path, we basically mean, getting from the place where the wave originates to where we're looking at. Like for this picture, it's at point P. So the path for, say, light ray 1 is from S1 to P, but then there's another wave that comes from S2, and so it has a different path. So basically what we want to know is, what's the path difference and how does it compare to the wavelength? Because the idea is that if you, as you can see in this picture, they didn't do it the whole way along the path, but in a path, for instance, like here, if this is R1, a certain number of wavelengths will fit on the path. And then if I do R2, I'm going to have to make it a little bigger. If R2 is R2, even though more wavelengths are fitting on the path, they still are at the same sort of phase when they get to point P, because at the end of that ray is when they get to point P. So like this would be P, and this would be P. So the R2 minus R1 is what we call the path difference, the difference in the path. And if that, so right here in this picture, it would represent this difference. If that difference in the path length is some multiple of a wavelength, like if it's 1 wavelength or 0 wavelengths or 2 wavelengths, then when the waves arrive at the location, they're going to be in phase with each other and they'll reinforce each other. And so this gives us constructive interference. Now, another possibility is, what if when they get to their location, they're doing exactly the opposite? So what if I have R1, and so my wavelength was like this, like that. Just excuse my not drawing it really good. Doing my best. So if this one, if we add up these two, you know that those two are going to cancel each other out. That's when we have destructive interference. And R2 minus R1 gives us the path length. And if that path length corresponds to, so here it is, delta L, if it's like a half a wavelength or 3/2 a wavelength or something like that, then what happens is the two waves are going to arrive exactly out of phase at that point, and they're going to experience destructive interference. That's something that's really important to remember, and we're going to come back to that in a moment. So we're sort of using the idea of water waves interfering when we're talking about this constructive or destructive interference, but it applies to any wave, and that's really important to remember. Here's another picture of the waves in the water tank, and again, seeing them interfering with each other, both constructively and destructively. So the reason that we talk about this is because there's this thing called the double slit experiment. And when we see the results of the double slit experiment, we actually see light waves interfering with each other both constructively and destructively. We also see the sort of spreading out of the light waves as they come from a source. So the way that the experiment worked is you first start with monochromatic light. Remember, that means it has a single wavelength and, of course, frequency. We'll send it through a slit first just to get it all nice and focused. And then it goes through 2 slits, which is why we call it the double slit experiment. Those 2 slits basically act like 2 separate sources of light waves, sort of like our S1 and then our S2 in those pictures of the ripple tanks. And then the light waves come from those 2 slits and they spread out as they move outwards across the room. And when they hit the screen, there's going to be a pattern of interference. And that interference isn't really what we might have observed. If we think about that experiment, your first thought might be, if I put 2 slits in a screen or in a barrier and I put a light in front of it, I should just get two bright spots on the screen, one in front of each of the slits. But we don't. We get this pattern right here, which indicates that the light is acting like a wave, where this picture would indicate that light was acting as a particle. Now, just in case you decide to try this at home, remember that this source needs to be monochromatic, so you can't actually use a light bulb because that has a lot of different wavelengths of light. You need a laser beam. And the slits have to be very thin. Probably can't make it on your own unless you cut something with a razor blade. You can't just take a pair of scissors and make two slits. So basically what's happening, again, in this picture is the light, as it comes through the two slits, is spreading out, and then these two wave fronts that are formed from the two slits are interfering with each other as they overlap, because the spreading out is called diffraction. That's another characteristic of waves. And what we see on the screen is a pattern of where the waves are constructively and destructively interfering with each other. Here's another picture of it. Just nice to see it visualized in a couple different ways. Okay, so let's try to understand what's happening. We're going to come back to our idea that it's the path length of the light coming from the two sources that's really important, because we found that a difference in the path length can be linked to conditions for either constructive or destructive interference. We're going to call that difference in that path length delta L. Now, if we imagine that the slits are relatively close together, which they will be, and the screen is a much larger distance away, this picture becomes a pretty good approximation of what's happening. And then this distance here, if we just go from this line and we draw a line down to the second ray and it hits at a perpendicular distance, this right here, which I already highlighted, is the difference in the path length for the two light rays. And so comparing that difference in the path length to the wavelengths is how you're going to determine at a particular location on the screen, am I going to get a bright spot or a dark spot? So coming back to our conditions for constructive and destructive interference that we came up with a couple slides ago, remember when the path length is related to the wavelength by a simple multiple, 1 wavelength, 2 wavelengths, 3 wavelengths, we have constructive interference. If the difference in the path length is some half of a wavelength, like 1/2, 3/2, 5/2, we have destructive interference. So we already knew that, but in the previous slide we found that the difference in the path length is related to d sine theta. D is the distance between the slits. And so now we pair this information in the first two with this, and substituting in d sine theta for delta L, these are our conditions for where we have bright spots and dark spots in our double slit experiment. Another thing that we sometimes like to find is what is the distance, the vertical distance for the, like where will I see a bright spot or a dark spot? So we start off with the idea that d sine theta is equal to m times the wavelength. This is for a bright spot, because that's the condition for constructive interference. Now, the sine of theta would be y over this distance here, this hypotenuse of our triangle. But if theta is small, which usually it is pretty small, we can say that the sine of theta is about the same as the tangent of theta. And so we can make this into d tangent theta is equal to m lambda. And the tangent of theta in this picture is y over d, where D is the distance from the slits to the screen. And so Y, which is going to be where the bright spots are, can be written as m lambda times D divided by little d. And so this is an expression we can use as well to figure out, okay, so for instance, the first bright spot, there's always going to be a bright spot in the middle. The middle one is m equals 0, but then if this was the first bright spot where m was equal to 1, we could put m equals to 1 there. Lambda is the wavelength of the light we're using. D is the distance from the slits to the screen, and little d is the distance between the screen, and we can just figure out where exactly are these bright spots located on the screen. Okay, so that finishes up for the double slit experiment, and then the next video is going to be on thin film interference.